All right. I hope you're not going to get any power outage during the lecture. Otherwise, I'm going to escort you outside the classroom. Couple of important reminders. Homework 1, due tonight, midnight. Make sure you don't upload on Gradescope a minute before the deadline because it gets very crowded. Same thing, don't rely just on Overleaf. It went down yesterday, we all know about it. So make sure that you have at least a local copy of your homework. And both for those of you here in the classroom and those who are watching the lecture, I received a lot of emails in the last 24 hours and Piazza posts regarding my office hours to meet for the project. I didn't forget about you. I will reply before going to sleep today, okay? So I got a lot of them after I sent that public post on Piazza, so I just have to catch up. Okay, so let's get this started. Today we're basically opening a new chapter in 224W. We're gonna start to talk about machine learning applied on graphs, okay? So the title of today's lecture is Message Passing and Node Classification. The material has been prepared both by Yure and Srijan Kumar, who was a postdoc in our group, and now is moving to Georgia Tech as a tenure-track professor. And this part of the course will last roughly 2-3 weeks. Basically, we are starting from how machine learning started on graphs long ago, and then in the next couple of weeks, we're gonna guide you all the way through basically the state-of-the-art of advanced machine learning on graphs, okay? But this lecture is necessary, to show you where everything started from and what are the basic techniques that even today you can apply with a lot of success on graphs. So, what is the outline of the lecture? Basically, we're gonna, everything will revolve around one main question. So, given a network which has labels on just a few nodes, how do we assign labels to all the other nodes in the network, okay? Let me give an example. So say we have an actor where some of the nodes identify fraudsters and some nodes are fully trusted. How do we find the other fraudster and the other trustworthy nodes, okay? I'm gonna guide you through a real world example based on this scenario, but I will show why it's extremely useful to be able to do this kind of classification. Now let's try to visualize the problem that we have in mind. So we have given some of the labels for our nodes. So we have green nodes, red nodes, and we have a lot of nodes for which the label is unknown. So we want to build, this magic machine that by the end of the lecture, hopefully, we're going to have understood how exactly it works. And then this classifier will be able to tell us the most likely labels for the missing nodes. Now, you might be asking, when is this kind of scenario happening? So if you went through any other course in machine learning, you will recognize this is a standard semi-supervised setting. So we have a few labels, not all the nodes are labeled. When does this happen in the real world? So you can think of this, for example, as a social network. And as you know, outside of the glamorous world of research, where we have a lot of labels and our data sets are very clean, the harsh reality is that it's extremely expensive to collect those labels. So what do? We just do random sampling. We do some kind of smart sampling where we obtain these labels, but they cover just a small fraction of the data. And then what we hope to be able to do after we collected that small fraction of labels is to come up with this setting where we can obtain trustworthy predictions for our graph, okay? So that's the scenario where we start from. And a lot of social studies, for example, start from this scenario where we can collect just a few labels and we want to be able to predict the rest. So what we're going to be talking about is this class of technique, and the umbrella term that we use is usually collective classification. So basically, the idea is that we're going to be assigning labels to all nodes in the network together. Okay, so we're going to be using the little information we have from the label nodes, and then we spread it around all the network, and we try to come up with a stable label assignment for each node. Now, what is the intuition? Why should this work? Again, think about any classic machine learning problem. You need some kind of inductive bias. You need somewhere where to get information that will allow you to do this prediction. Luckily, in networks, a lot of correlations exist, okay? And basically what we're gonna be doing throughout this whole lecture is leveraging those correlations. Okay, I'm going to go more in detail and explain some examples of these correlations, but the good news is that they exist, so we can leverage them to build a predictor. The three main techniques that we're going to be talking about today are relational classification, iterative classification, and belief propagation, and they are basically in order of how advanced they are. Okay, so we're going to be starting from the simplest one and work our way to the belief propagation. So let's go to the correlations, as I was mentioning before. What are they and why are they so important? First of all, we know that individual behaviors are correlated in a network environment. So basically it's the case of homophily. I'm going to explain in detail what it is, but you can think that people that have similar individual characteristics, they will end up more likely to be connected in a social environment, okay? So say this is going to be based on age, it's going to be based on your job, on your race, and so forth, okay? Conversely, you also have an influence factor. Basically, if you are tied in a social network, then there is a chance that someone is going to be influencing your taste in movies, in music, and so forth, okay? So all in a sudden, also your individual characteristics will evolve, will change. So these are the two main type of correlations that we are going to be leveraging. Unfortunately, as any scenario, this is not a perfect, clear-cut distinction. In reality, sometimes there are also confounding factors that both can affect your individual characteristics and your social connections, okay? So there will be some external environmental factors that will change your taste or will decide if you establish friendships or not. But likely, most of the times is the case that these correlations are very strong, so they're a very good signal to train our classifier. So now let me give you some examples of what are these correlations. So the first case that I was making is homophily. And homophily is this idea that individuals tend to associate and bond with similar others, okay? So you can rely to these famous sayings that birds of a feather flock together. People that have taste in common, they tend to bond more easily together. And this has been observed for decades on a myriad of studies that you can find, both in network studies, social networks, and so forth. And these studies have been performed also on a variety of attributes, okay? So depending on the context, you will find that, age is the driving factor for people to, connect to each other, gender, organizational role in a company, and so forth. So we have a lot of evidence that homophily plays a factor. So let's have a running example that we're going to be keeping for the rest of the lecture. So for instance, people who like the same music genre are more likely to establish a social connection, right? So maybe they're going to be meeting together at a concert, or maybe they're going to be interacting online in music forums and so forth. So their individual characteristics lead them to meet like-minded people. Conversely, as we were saying before, your social connection can influence the individual characteristics. So likely we're going to be having basically a couple of lectures covering exactly this topic, so I'm not going to go in depth today, but just keep it in mind that this happens and it's a very well-studied phenomenon. And the example here is that we basically flip what we had before. So say that I go around and I tend to recommend my very weird musical preference to my friends, and eventually I always find someone who starts to like the same music I like, goes to concert with me, and so forth, okay? So these are the two main correlations that you can think about. All right, some examples. So let's think about a real social network. This example actually comes from the book that we point to on the website oftentimes. So this is a real social network. Nodes are people. The edges are the friendship that they established. And the node color is the race. So as it has been studied oftentimes, and I think this is a subset of a Facebook graph, people tend to be segregated by race due to homophily, okay? So for instance, if you take my Facebook graph, possibly half of them are my Italian friends. So there is clearly some homophily due to the race and the fact that I was born there, and most of my friendships are back home. Okay? Any questions up to now, or shall we go to the classification? Okay, let's move forward. So let's go back to the example that we had before, basically. So how do we leverage now this correlation that we observe in networks to help predict our node labels? So the scenario here is we have what usually we call a sign network. So the green edges, we label them with a plus. The blue edges, we label them with a minus. And then these beige, sorry, not edges, nodes clearly. And the beige nodes, they are unknown. They have an unknown label, okay? So how do we predict the remaining labels in this graph? And I want you to keep in mind already from now that here we're basically talking about a binary class, but you can imagine of training multiple classifiers for the same network based on different classes, okay? So very similarly to what you will do in a multi-class problem in a standard machine learning dataset, you can do exactly the same with a graph, okay? So you're gonna basically be training one classifier per class. Now, for the sake of simplicity, today we're gonna be talking mostly about binary class problems, okay? So back to the problem, how do we predict our labels for the beige nodes, okay? So the idea is what we were mentioning before. So when we match together both the homophily and the social influence, we come up with something that usually is called guilt by association. So if I'm connected to a node with label X, then I'm likely to have label X as well, right? So the example I was making before, you take my Facebook graph, there is a high chance that one of my connections will be another Italian person, okay? So very similar, guilt by association of being Italian. Now, other examples that are going to be more useful throughout the lecture. So, for instance, malicious or benign web pages. So this is a very common problem. Usually, malicious pages tend to link each other, okay? Just to increase their own visibility, look credible, and also in the hope of ranking higher in search engines, okay? So, and rarely these malicious web pages will be linked by very trustworthy websites, okay? So we all hope that the New York Times is not going to be pointing to a lot of websites containing fake news, for example, okay? So this is the intuition. Towards the end of the course, we're also going to be seeing a more advanced technique that has been studied for decades, which is PageRank, and we're going to be seeing basically how to distinguish between malicious and benign web pages, okay? But this is a nice example to keep in mind because that's, where a lot of these classifiers have been tested at the very beginning. Okay, so we understood now what is the motivation. Basically, we have a classification label on our object O in the network, and we have different sources of data, different features that we can leverage. First of all, we can have features attached to that node, right? So we were saying if that graph we saw before is a social network, you will have the gender, you will have the age, the nationality, and so forth. So you can have a wide vector of features attached to the node. Then another set of features that we can leverage are the labels of the objects in the neighborhoods of O, okay? So going back to the previous slide, basically we're gonna try to be using this guilt by association. If my neighbors all have the same label, then there is a high chance that I will have the same label as well. And last but not the least, we can also try to use the features of the objects in O's neighborhood, okay? So basically, we're making this more and more advanced, more and more complicated step by step, okay? The easiest is to start from the features of O, and then, we can start to use the network features as well. So let me ask you a question. What are we actually doing if we only use the features of O to do our classification problem? What do you think our classifier is doing there? Like, does it make sense to call it collective classification if we only use the features of O? Right? Okay, I see a lot of heads shaking, cool. So the answer clearly is no, right? Basically, what we're doing there is we're not leveraging any network properties, so we're just training a plain classifier on the features of the nodes, okay? So we're missing completely the topology of the graph. We're basically missing the opportunity of using it, okay? All right, so now let's try to formalize a bit more the problem. So the way in which we're going to see it is we have our W matrix, n by n, which is an adjacency matrix. It can also be weighted. So we can have a simple adjacency matrix with 1 and zeros that signals only the connectivity between the nodes, or we can also have it weighted basically with how strong is the tie between two nodes, for example. And then we have our vector y, basically it's the label vector, and the entries of this vector could even be this 1, so the positive label for a node, -1, a negative label for the node, or the case of the unlabeled node that we want to try to solve with our classifier, okay? So again, the goal is to predict the unlabeled nodes, which are likely positive. Now, the applications, I mentioned a few of them that just came to my mind. You can find a variety of papers out there that really solve the craziest scenarios that you can think of. So collective classification has been used in document classification. For instance, if you think about web pages, they connect to each other, so there is this underlying graph structure. It has been used for part-of-speech tagging, because you can imagine that you can parse a phrase, and then you will be getting your parse tree, and that can be used as a graph structure. Limb prediction, 3D segmentation. This is an example I've made, for instance, during the recitation session during the first week. It's very interesting to use basically what we call the scene graph today. So if you have multiple objects in an image, then you can connect them when they are close to each other, or you can try to encode if an object is in background and in foreground, and these are very interesting graphs to work with. So if you are planning to do that in the project, I recommend it to you. It's going to be a fun one, and so forth. Okay, so a lot of different applications where collective classification can be used. Now, let me give an overview, and now I'm going to guide you step by step how we actually perform the collective classification, okay? So we start from this Markov assumption, first of all, which basically tells us that the label yi of our node I depends on the labels of its neighbors ni, okay? So once again, this is just encoding this idea of guild by association that we were mentioning before, okay? And a standard collective classification pipeline involves 3 main steps. The first one is a local classifier, which will assign the initial labels. So you can think of that basically as a bootstrap step, okay? So for the labels, for the nodes for which we don't have labels, we're going to be trying to use a local classifier to estimate what is the best label. Then the second step is we're going to be using a relational classifier, which is able to capture the correlation between the nodes. So what we were talking about before, the homophily, the social influence, and so forth. And last but not the least, the collective step, which will perform collective inference. And what it does, it basically propagates the correlations through the network, okay? So we don't only want to stop at the level of using only our neighbors, but with multiple iterations of our collective classification, we're going to be able to spread the contribution of the other neighbors over multiple steps until we hopefully reach a convergent state of our algorithm, okay? So all the algorithms that we're going to be seeing today are iterative, and also they are an approximation. We're going to go more in detail about that, okay? So now let's try to dissect each single phase that I was talking about before. So our bootstrap step, the local classifier, which assigns the initial labels, does the following. It basically predicts the labels based on the node attributes or features. And it's just a standard classification task. So it's basically the question that I was asking to you before. If we stop our collective classification here, we are not using any feature from the graph. We're just using the node features, okay? So it does not use any network information. You can train any kind of classifier that you want there, KNN, well, even the simplest one are going to be working very well. Then second step is our relational classifier, and what it does is it learns a classifier to label one node based on the labels of and the attributes of its neighbors, and this is where the network information is used. Question?
So when you talk about the local classifier, you say it doesn't use any network information. Could you have as a feature like the degree of the node, for example, for features that are dependent upon the network?
Yeah, absolutely. So great question. The question is, can I also use some features from the topology of the graph? The answer is yes. There is no clear-cut rules of how each single step should be implemented. But basically, the expectation will be that if you stop at that level, I wouldn't call it collective classification because you're just using local features of your node. But yeah, absolutely, you can do that. Okay, so second step is a relational classifier. That's where we bring in the network information. And then the last one is this propagation of our correlations through the network. And the key here is that we're going to be iterating over multiple steps. And then we basically iterate until the inconsistency between the neighboring labels is minimized, because we're going to be seeing these probability values to fluctuating over the different iterations, and we're going to be stopping when these fluctuations are very small, okay? Or after a certain amount of steps, when basically we don't have any more computational resources to use. And as expected, the network structure here substantially affects the final prediction, okay? So you can think of, if you're running this step on a click, it's going to be completely different from if you're running it on a star-shaped graph, right? So on a click, you will be expecting almost this uniform spread of the probabilities among the different nodes. If you're running in a star graph, basically the label of your central node will be the one that influences most of the other labels in your graph, okay? So it plays a key role. Now, as I was mentioning before, everything that we're going to be seeing today is an approximate inference technique. The reason is the exact inference is extremely expensive. So first of all, we can find exact solutions only if the network satisfies certain conditions. It has been proved that it's relatively easy to obtain that in trees. There are some conditions in polytrees where it works. We're not going to go into detail about that today, because class focuses on graphs, and I'm going to be telling you what happens when you do collective classifications on graph, okay? But just keep in mind that if you try to perform exact inference, that's an NP-hard problem. And I try to write here an intuition of what is the difference between exact and approximate. The key point that I want you to keep in mind is that the exact solution takes exponential time in the number of nodes, right? So as soon as you start to have a few thousands of nodes, forget about running this on a real graph, okay? So that's why we fall back to these approximate inference techniques. The good news is most of the times they work extremely well, okay? And the solutions you're getting are so close that it doesn't really make such a big difference. So that's how we're going to be focusing on them. So let's start from the relational one, the easiest, okay? So what is the problem setting? Again, we're trying to predict our labels yi. Each of our node I has a feature vector, and some of the labels are given. So now, how do we find the missing labels for our beige nodes, okay? And the basic idea is that the class probability of our node I is a weighted average of the class probability of its neighbors, okay? And what we do is, for the label nodes, we just initialize with the ground truth, okay? So we have the labels. It wouldn't make any sense to initialize it in a different way, right? We know that those labels are correct. And then for the unlabeled nodes, what we do is that we initialize the y uniformly, okay? So we're going to be basically assigning to all of them 0.5, and then through each iteration, these probabilities will converge towards the right value. And the way in which we do this processing is we're going to be updating all the nodes in random order until the convergence or our maximum number of iteration is reached. Now, doing the updates in random order is not the only way you can do it. It has been shown empirically that it works very well in most of the cases. So that's why we're going to be sticking to that strategy, okay? But there is no clear-cut reason why you should be doing only random ordering. And at the same time, keep in mind that the order will be affecting the results that you will get. Now, once again, these kind of local effects are exacerbated when you're working with like a toy example, like most of the things that we give you for homework, for instance. But when you're working on a very large graph, usually this ordering will not be affecting a lot the label distribution you will be getting on your graph, okay? So that's why sticking to a random strategy is most of the times good enough. Question?
For our label nodes, why are we initializing by like uniformly? Can't we do something like train a classifier on the label nodes, and then based on the basis of that classifier, we classify the unlabeled node? Great question.
So the question is, why are we doing this uniform assignment to y's? Why don't we use a classifier? Why don't we even use a prior, right? Okay. The answer is, this is the most generic case we can think about. Now, if you have a prior that you trust, absolutely, go ahead and try to plug that. One reason is, if your priors happen to be very unfortunate or very skewed, it might be taking you many more iterations compared to what we're seeing today. So from the uniform assignment, it usually takes you fewer steps to converge to the solution, okay? But if you trust your priors, absolutely, go ahead. Okay, so now let's go through the few formulas that we're going to be seeing today for how to perform collective classification. So what we do is, for each node I and label C, what we're finding is what is the probability that the state of our node I is going to be equal to C, okay? And what we do is, first of all, Ni is the number of neighbors of I, and then W is our adjacency matrix that we were talking about before. It could also encode the weights. And then this is the probability, basically, that our neighbors are going to be having the label C, okay? So what we do is, basically, we take a weighted average of the labels of our neighbors, and then we normalize by the number of neighbors of I, okay? And that's our label assignment. Now, the challenges here are the following. The convergence is not guaranteed, so it's an approximate solution, and we don't know if it's going to converge. And the other big problem that at least we're going to be able to solve in the next parts of the lecture is that this model is currently not using the node feature information at all, okay? It's just currently using the network information, so the labels of the neighbors, okay? So this is a big shortcoming. The first challenge, even though it looks scary because we don't like algorithms that don't give us guarantees, once again, it has been shown empirically that this lack of convergence happens very rarely. And also what you can do is, as it's always a very good rule of thumb when you're applying machine learning, is basically plot over time what is the behavior of your weights, what is the distribution of your labels. And if you see that these fluctuations are just periodic and they're not increasing over time, then you know that you reach some kind of convergence state, okay? And that's what people do a lot of times in this case. Question?
So when we are iterating through the nodes in our graph, are we picking the nodes randomly, or are we going through some sort of sequence that repeats until we converge?
Let me repeat the question so we find out if I understood correctly. Your question is, shall I take the nodes, my neighbors randomly when I apply the formula or not? Is that what you were asking?
So it basically says repeat for each node I and label C.
Okay.
So when we're going through each node I, are we going through these nodes in our graph randomly, or is there a specific...
Randomly, yes, correctly. So it's what I was saying before, like this random update strategy, it has been shown to empirically work very well, and it doesn't seem to affect a lot if you do it instead in order. Thanks, great question. Okay, any other questions, or? Okay, let's move forward. So we mostly want to keep this shortcoming in mind, the fact that this model is currently not using our node features, okay? Now let's go through an example so that we can apply what we just learned. So we give 0 as a label to our blue nodes, 1 to the green ones, and then we did our uniform assignment to the beige nodes, so our 0.5. So first step of our iteration, we take one node randomly, so we're working with node 3, and we update the weight to 1/3. So the reason is 3 has 3 different neighbors, right? It has 4, it has 1, and it has 2. 2 and 1 have 0 weight. 4 has 0.5 because it comes from our uniform assignment. We divide by 3, and then we get 0.17, okay? So very simple math. And we keep on applying this, so now we update the weight for 4. I'm going to let you go through the slide and convince yourself that hopefully I haven't made any mistake with simple summations. So this is the first configuration we get after iteration 1, okay? Now, we want to run this again. The reason why intuitively you already know that you want to run this again is some of these probabilities are already quite extremized, right? So we know that most likely node 3 will be a negative label, node 9 will be a positive label, but for instance 4 is sitting in a limbo now between 0 and 1. So we know that we want to keep on updating this until we hopefully are going to reach a more stable solution. So now we apply iteration 2. As you can see, the weights are being updated. Iteration 3 updated again. So see, 5 and 3 are slowly converging towards probabilities of 0 or 1, but unfortunately our node 4 stands in the middle, and after iteration 4 is still at 0.51. So what happens here is that once we are satisfied and once we run enough iterations, we want to turn those probabilities into actual label assignments, right? So at the fifth step of the iteration, we found out that our scores are stabilized, so they haven't been updated anymore. So we stop our algorithm, and then now we can assign the labels for node 5, 8, and 9, so they will be positive because the probability is above 0.5. Same we can do for node 3, because the probability was 0.16, so it's below 0.5. But unfortunately, again, node is sitting in between because it's equal to 0.5. So as we said before, the convergence is not guaranteed. We know that the algorithm stopped because there weren't any weight updates, but it wasn't able to reach a decision for node 4. Now, given that this example is so small, you can already intuitively get the idea why 4 wasn't able to receive a good label. If you think about the community detection that we talked about last week, basically node 4 is like a bridge node between two communities, right? So here is the negative community, and on the left side you're going to have the positive community. So node 4 is getting pretty much equal contribution of positive and negative, so we are not able to assign it a proper label. So say now we have also prior about the features, like the question that you had before, then we can use it to break the ties and decide which label to assign to node 4 in that case. Okay? Question?
So when you do the iterations, the second iteration has the same order based as the first one?
Yes, in this case, it's exactly the same order, but again, not necessary. Yeah, you might basically be losing, be adding a few steps because the choice of the ordering is unfortunate, but if in your configuration you will be converging, the chances that you will be converging with a different order are extremely high. Okay, so it just wastes a bit of time, no more than that. Question?
So you're just like, each node is like the average of the other probabilities in each step.
Correct.
So could you just solve the linear system?
Absolutely. So in this case, you can solve the linear system. And what I was showing to you before is, in some cases, you can find an exact solution. So I think this one would be possible to solve with variable substitution. It's just feasible because this graph is extremely small. You will never dare to do that like already with 1,000 nodes. And these cases are not very interesting to classify mathematically because you could do it by looking at it. So in the homework, just to give you a spoiler, this is the size of graph we're going to be asking you to do collective classification on, okay? So that you can definitely double check if what you're implementing is correct or not, okay? Any other questions, or we move forward? Okay, let's go. So we explained why a relational classifier is not as powerful as we would like because we are not using the node features. So now we're going to introduce iterative classification, which likely brings in also the node features in the picture. So the main idea is that not only we classify our node I based on the labels of our neighbors, but also on the attributes of our neighbors, okay? So that's the key difference between the two techniques that we're gonna be seeing today. What we do is, so for each node I, we create a flagged vector A of I, which contains all the node features. Then we train a classifier to classify using that flagged vector, and then node may have various number of neighbors. So basically what we do is we decide a strategy to aggregate those features, okay? So we can decide, for instance, okay, our aggregator is gonna be a count, like how many of our neighbors have that feature. So say you're using gender as a feature, how many of our neighbors are female, how many of our neighbors are male, and so forth. Or you can think of a lot of different aggregation strategies. And the reason why we have this lecture at this point of the course is because we're going to be talking about graph neural networks in a week or so, and we will see that aggregation strategies play a key role in these graph neural networks, and the idea comes from there. It hasn't been invented like 3 years ago with GNNs, but it predates them from the era of collective classification. So now let's go through the phases, the same one that we talked about in the beginning. Now we apply them to our iterative classifier. So we start from our bootstrap. And the bootstrap is we do this conversion of each node I into a flat vector of features, and then we use a local classifier to compute the best value for y of I, okay? So back basically to the question that you had before. Now in this case, we really want to use as much as possible either a local classifier or some prior information that has been given to us about the node of that graph. And then in our iteration phase, we do the following. Basically, again, we iterate until convergence. And for each node I, we do an update of the node vector, and we update the label assignment, and then we iterate until the class assignment stabilizes, okay? So this is very similar to what we did before with the relational classifier. The only key difference is that we're also using the feature vector, okay? Again, similar to before, convergence is not guaranteed. In that case, in the worst case, you're gonna be running this for a maximum number of iterations. And I come to your question immediately. Last remark is, we will be seeing this kind of trade-off till the very end of 224W. We're gonna be seeing this for page rank, we're gonna be seeing this in influence maximization. It's very common that when you want to find an approximate solution, you iterate, and then you come up with a convergence criterion, okay? So you decide, I accept my weights fluctuating a certain epsilon, and then when this configuration has been reached, you decide to stop. Question?
So in there you have written like for each node I, you update node vector AI. So what does that update mean?
Okay, so you're asking, what does it mean to do this kind of update, right? Okay, I will show you immediately. Basically, the intuition is every time you change the labels of your neighbors, this will affect the vectors maintained by your neighboring nodes, right? Because these vectors will contain, okay, how many nodes with incoming edges are male or female, for instance, in the gender graph, okay? But we're gonna be seeing now with an example, and this is with web pages. So we're back, to the example we were making before with malign or malicious or benign web pages. So what is our feature vector here? So what we're gonna be using is a very common feature representation, which is called bag of words. Basically what we do is our vector will encode if a certain word appears in the document or not, okay? So you can decide that vector to have an arbitrary size. You can decide to only to capture the top 100 words, top 10,000, and so forth. But that's our node vector. And then our baseline is we train a classifier to classify the pages based on the words. Okay. So here is the example. It's basically the one encodes the fact that that word appears in the document or not. So we can build all these vectors for our different nodes, run our classifier, and then the classifier will tell us, okay, these two pages have label B, and these two pages have label A, okay? And you can see why basically there is high similarity between these two vectors and higher similarity between the two pages on the left, okay? Now, if we're not using the link structure between those web pages, we're back to what we were saying before. We're not doing collective classification, so we're not using the graph structure at all. We're not leveraging it, okay? And in reality, you will see that now we have a misclassification because our ground truth tells us that all these three pages should have label B, and only this page should have label A, okay? So intuitively, if you see the graph structure, you see that these three pages on the left are very much interconnected, so it makes sense that they have the same label, okay? So how can we improve now? How can we make sure that we overcome the problems coming from our baseline classifier and that we can fix that misclassification? So what we want to do is we want to bring in also our network features, okay? So as we said, each of our nodes now maintain a vector of neighborhood labels. So for instance, in this case, we chose the existence aggregator, which basically will tell us a certain feature is 1 if at least one of the incoming pages is labeled A, and you can do the similar definition for all the three elements of the vector, okay? So I of B will be 1 if at least one incoming edge is from a page of label B, or one outgoing edge goes to a page of label A, and so forth, okay? So now we build our network feature vector, and all of a sudden we're able to use more information. Now, how do we do this? How do we make this work better? Now, we the strategy is very similar. So first of all, as we said, we do our training, and in this case, we're not training only one classifier. So we have now two different classifiers. One is the baseline classifier that we were talking about before, basically the one that only uses the word vector, okay? So the green circles in our drawing. Now we have also another classifier which is using both the word and the link vectors, okay? So that takes all the features into account. Now we do our first step of bootstrapping. So we use our classifier trained on the word vector to do the assignment. It will give us exactly the same label assignment that we had before. So 2 B's on the left and 2 A's on the right. We know that there is a mismatch because the ground truth for this page instead is B. So we know that it's wrong using only the words. Now we do our iterations, and basically we update our relational features until this converges to the setting that we were hoping for. Okay? So now we're using our red circles, we're using our network features, and now our classification will tell us that the label for that page should be instead B. Okay? And we continue until convergence. Basically, we continue until convergence because as soon as we reassign the label for this page, so this is the question that you had before, now we have to update the network features for each page, okay? So now all in a sudden, what before here was a 1, because this page was labeled as A, and this page has an incoming node labeled A. Now when we do the update, this becomes a 0, and this one becomes a 1, because the incoming edge is a B, okay? And similar, all the updates happen also on the left side of the graph. So we continue until convergence, we do our classification, and we reach we reach convergence. So this is the final assignment of the labels to the pages. Any questions? Make sense? Okay, awesome. So let me guide you now through an example so that you can see how this is used in the real world. So this is a very recent paper published in our group. So it's basically an application of this iterative classification framework, and it's used to find fake reviewer and reviews. Okay, so it detects who leaves fake reviews on websites and who are these fake reviewers. And the reason why the review sites are very attractive for spammers is because getting a 1-star increase in your rating also leads to an increase in revenues, okay? So 1 star is usually observed to increase revenues by 5 to 9%, which is a lot of money. So it really justifies the fact why people are putting so much effort to spam these platforms, okay? There are also the reasons why there are spammers in this platform. They not only try to, boost the rating of certain items, they also try, to defame or to spam other items from competitors so that there is a bigger gap between the reviews of the two, okay? And given how much money this phenomenon drives, there is a black market of paid spammers. You might have read this. There was a news, I think, Facebook was probably the biggest organization having groups where people were arranging paid spam farms. Okay, so Facebook was not even aware about that, and I think they shut down a lot of these private groups where these paid spammers were meeting and deciding the different strategies. Okay, so it's a very wide phenomenon, more than you might expect. So why is this a hard problem? It has been studied, even before we even thought about using graphs. Clearly, the first thing that will come to your mind is you do behavioral analysis, right? So you try to find individual features, geographic locations, and maybe there are countries where you expect these spam factories to be more productive, when they log in, the session history, and so forth. You can also try to analyze the language in the reviews, okay? So if they use superlatives, what is the rate of misspellings, how many words are agreeing with the quality of a product, and so forth. Unfortunately, these have become very easy to fake, both individual behaviors and the content of the reviews. If you've been following a bit the state of the art in natural language processing, today we have very powerful language models that basically allow you to generate reviews that sound much better than my English. So it's very scary. So given that these features are not reliable anymore, we had to think about something more powerful. So luckily, it's much harder to fake the graph structure. And the graph structure, what it does is it captures, the relationship between the reviewers, the reviews, the items, the stores, and so forth. Okay, so the fact that, as we were saying before, similarly to what web pages do, now if they are malicious, then they tend to link to each other. We see something similar also with reviewers. Basically they interact a lot with each other, or we see that people from similar areas, similar session histories, they all tend to be identified in a very small area of the graph. So how can we find them in our graph structure? So that is very similar to what we have been seeing before within the iterative classification. Is just some additional tricks to make it even more powerful. Now, one advantage in this case is that we can represent our graph as a bipartite graph. Okay, so it's a bipartite graph because we have users from one side, and then in this case, this is a generic app store where you can download apps for your smartphone. So these users are leaving reviews for the different apps. Okay, Gmail, Pokemon, and a malicious app. Okay, so what we want as an output from our algorithm is the set of users that are giving fake ratings because we want to kick them out from the system. And we can represent this as a sign network. So our red edges will be the negative reviews, and our green edges will be the positive reviews. So the key difference compared to what we have seen until now is that not only we have features on the nodes, but we're also carrying features on the edges in this case, okay? Because we have weights on the edges, and we're gonna be having weights on the reviews for an item, and we're gonna be having some sort of score that tells us how much we can trust a reviewer in our platform, okay? So let's make this a bit more formal, and what are the scores that we're gonna be using? So our users will have fairness scores. So this score will tell us how fair are the reviews that usually that user leaves. The products will have some sort of goodness score. Once again, this goodness score will be between -1 and 1. And the ratings will have a reliability score, okay? So each rating will have a score that will tell us how reliable is that review. And at the very beginning, all these values are unknown, okay? So we try to start from a blank slate, and we don't assign any weight. So what we do is, how can we now calculate the values for all the nodes and the edges simultaneously, okay? And as I spoiled to you before, the solution is a more advanced version of iterative classification. So what we're gonna do here is that we're gonna be fixing 2 features at a time, and then we try to update the remaining feature, okay? So for instance, if you want to compute the fairness of a user, what we do is that we fix the goodness of an item, we fix the reliability of all the reviews, and then what we do is that the fairness is nothing but the sum of all the reliability of the reviews left by that user, okay? And similarly, we can compute now the goodness by fixing the fairness and the reliability, so that now the goodness will be nothing but the score assigned to that review times how reliable is that review, okay? So if the review has very low reliability, no matter what is the score, it's not gonna be impacting the final goodness score for that app, okay? So this is the key insight from that formula. And last but not the least, when we fix both the fairness and the goodness, then now we can do an update on the reliability. So what we want to do here is, how fair is the user who gives the rating? And it comes from this side of the equation. So we have a weight, how much we care about that feature. So our gamma 1 times the fairness of the user plus gamma 2 another weight times how close is the rating from the goodness of the product. So I'm coming to you right away. So what this part of the equation is capturing is how much your review is diverging from the common opinion of the quality of that app. Question?
Why do you choose to use the 1 norm for the score versus the goodness versus like the 2 norm, or basically just like a squared difference?
So I think your question is, why do we use the goodness, the ranges between -1 and 1, and why the ranges for reliability is from 0 to 1? From what I recall, is only to make the math look slightly easier. But you can use any kind of normalization here. What you care is the size of the range, not the actual values that you get. Okay, so this is just to give an idea that you can improve over the standard iterative classification that we have been seeing until now. And in this case, it works with 3 different features. Now, after we start with our initialization, so we give 1 to everything. Okay, so as we said before, we don't use any prior, we don't use any classifier. We bootstrap in a uniform way, and then we go step by step. We fix the rest. We try to compute the goodness, and already we see that the goodness of these 2 apps is much higher than the malicious one. We continue to compute that, and then eventually we're going to be converging to a state where the goodness reflects the quality of an app. We were able to identify 1 fraudster, so our evil node hub there has a very low fairness score, while all these other nodes have a very high fairness score. And then in that way, we're also able to now reweight all the reviews given by the evil node with the level of reliability of that review, so that they will not actually impact the scores of the good apps. Okay? Now, one question that you might have now is, isn't this also capturing the fact that if my taste is weird, I might be confused as a fraudster in the network, right? Okay, I see some heads nodding, so I think I wasn't the only one thinking that. So the answer is yes. So it has this kind of shortcoming. Now, why is this not a problem in reality? The reason is we're working with very large networks with a very large amount of users. So in this case, yes, it would be possible to basically take one user, tweak, and make sure that he or she reviews only certain apps, and then these reviews will be in disagreement with everything else, and then we might mistake the user as a fraudster. In reality, what happens is that there is always a very small number of fraudsters in a network, okay? So it's much easier now to identify them, and there will always be groups of people that no matter how you think peculiar are your tastes, there will be someone who has similar tastes to you, okay? So in that case, they will not be detected as fraudsters. There was a question or no? Awesome. Okay, let me show you now what happens on when this was applied in the real world. So nice properties, first of all, are this is guaranteed to converge. One of the reasons is because we are working on a bipartite graph. I will put a link to this paper in our suggested reading so that if you're curious, you can see exactly how this has been proved. The number of iterations till convergence is upper bounded, so another very nice property. And the most important is the fact that the time complexity is linear in the number of edges in the graph, okay? So this is something that is definitely possible to apply on a real world graph. So for this reason, we tried it on Flipkart, which is, if I recall correctly, one of the largest e-commerce platforms in India. Correct me if I'm wrong. And what this algorithm was able to do is that out of the under 50 users that had the lowest fairness scores, under 27 of them were actually real fraudsters. Okay, so like the platform knew already that they were fraudsters. And even better, the algorithm achieved 100% precision till the top 80. So the first 80 fraudsters that it identified were all actual fraudsters on the platform. Okay, so it was tested in the real world with a lot of success. Questions? Okay, then there you go.
Can we also integrate the information if we have, suppose, between the users' interactions? Like suppose there is a platform where users can also follow each other. So if suppose a fraudster like gives a negative rating to a good app, and there is some other people are following him or her, and then they like because of the influence of that user, they also give like kind of a negative rating.
Great. So your question is, can we also leverage the underlying social graph of how these users are interacting with each other? The answer is yes, you can. The reason why it has not been applied here is that if you think about it, you will be losing this nice property of working with a bipartite graph. All of a sudden, you will be having edges between the users, right? So then you start to lose the properties that I was talking about here. So as anything, the more data you bring in, the harder, the more advanced makes your technique. But I wouldn't be able to tell you off the bat if we will be able to make that scale to something as large as Flipkart by also using that feature. But yeah, absolutely. As usual, the more data, the merrier. Question?
You said this method of detection is hard to circumvent, but I'm thinking if I were to just rate a bunch of good apps that I don't care about positively, just increase my trust rating, and then also do fraudulent activity on the side, wouldn't that?
Right. Great question. So the idea is, what if I try to behave as a good user on the platform, give a lot of good reviews to the good apps, and then selectively give good reviews also to the bad ones? Like in some sense, what that will do is it will just skew the distribution of the fairness scores. So it will probably make you closer to 0.5. Like you will not have something as extreme as this fairness score dropping to 0.1, but you will just be, on the tail of the distribution. So if anything, we don't really care about what is the fairness score that we give to a fraudster. We just care if you are in the bottom 10 percentile. Okay, so sure, like you can always try to trick these systems that try to detect fraudsters, but I think it would be a lot of extra effort to not be detected. So, but definitely I think one of the hard lessons learned by this community is that people always find a way to circumvent any kind of system put there to find fraudsters or spammers. And another key thing to keep in mind is the fact that each one of these platforms have to do a very good job at not allowing a lot of random users or bots to register. Because as soon as you do that, if you can skew the distribution of the users by having half of them to be fake and bots, then all of a sudden all these assumptions they will go away, because they will not be the minority anymore, so you can really steer all the all the bias on the scores in that way. Okay? Question?
When it says that the algorithm's guaranteed to converge, is that converging on kind of a global optimum, or just kind of a local optimum?
So the question is, will this solution converge to a global optimum or a local optimum? From what I recall, this problem formulation is not differentiable, so I don't think there is a concept of local and global optimum here. I would have to point you to the paper in case there is more detail, but from what I recall, no, that's not the case. It should converge to the only global optimum that you can find. Thanks for the question. Anything else? Okay. Then let's jump to the last part of the lecture, which is we're going to be talking about belief propagation right now. So we have seen relational classifiers, iterative classification, and now we're going to be talking about loopy belief propagation. Now, what is belief propagation? It's a dynamic programming technique, and what it does is it basically answers conditional probability queries in a graphical model. Now let's try to dissect this statement and make it easier. So it's an iterative process in which every neighbor of variables talk to each other and they're passing messages. And what these messages contain is basically, if I myself am variable xi, I believe that you, variable x2, belong in these states with different likelihoods. So the way in which it works is like you're in school and you're trying to cheat and passing a small piece of paper during the exam. The state of this node does not depend on the belief of the node itself. It depends on the belief of all the nodes surrounding it. Okay? So that's why it's called message passing. What happens here is that every surrounding node, every neighboring node passes a message and tells to node I believe you should belong to this specific label. Okay? And we're going to be seeing why formulating the problem in this way comes with some very nice properties. Once again, this is an approximate inference approach. So it's iterative, and we stop only when we find a consensus. So only when the fluctuations in the variable assignment is small, and only at that time we calculate our final belief. Okay? Now, let's walk through much easier examples so that we can see what is going on. So suppose that we want to solve this very trivial task. We want to count the number of nodes in a graph. You cannot use snap now. You just have edges and nodes. How can you do that? So the condition that we're going to be imposing here is that each node can only interact basically pass messages with these neighbors, okay? So what we are doing here is that we are restricting the scope where our algorithm can work. The reason why we do this is not because we like to complicate our lives, but if we go back to the argument that we made at the beginning, we need to simplify these algorithms in order to make it able to run on very large networks, okay? So what I was saying before is when we move from exact solutions to approximate ones, what we need is, we need these aggregation functions that we talked about before, like existence or counting, so that, we can aggregate the messages. And we also need a way to focus not on all the nodes in the graph, but only on the ones that have most of the effect. So in this case, they will be only the neighbors, okay? Now, let's go back to our task. How do we count the number of nodes? We have this example graph. It's just a straight line. And for now, I'm going to ask you to ignore the potential issue coming from the fact that if a graph contains a cycle, this process will not end, right? Because this message will keep on going around, and we will see how we do this count. But you can imagine that the counter will just keep on incrementing, okay? So we're going to then talk about why loopy belief propagation actually works with graphs that contain cycles. But we come back to that later. So how do we do this? So each node listens to the message from the neighbors, and then it updates the message and it passes it forward. So let's turn our nodes into cute, resembling figures of humans. I promise I didn't do the drawing. So what this node sends a message to the node in front and says, okay, there is one node after you, okay? Well, message goes through. Now this node will say, okay, I know that there is someone behind me. I'm talking to the person in front of me, so now we'll tell you that there are two nodes after you. Now, I'm not going to guide you through the whole example. Basically, you generalize it. And the idea is that every node can say, okay, there is one on me plus all the people behind me, and this is the number that I will pass to the person in front, okay? So you arrive at the other side of the chain, and now we know that counting the node itself, this chain is long 6. But in this case, only this node will know the final state, right? Now, only this node is aware of the actual length of the graph. So now we need to backtrack. So we walk the solution back, generalize it, and then we arrive to the state where now everyone is able to know how many nodes are in this graph, okay? So this is the most basic concept of message passing that you can think about. In this case, is used possibly not for the most glamorous task you can think of. What we're going to be seeing in the following weeks is that this is a very powerful primitive, because now instead of passing around how many nodes there are in the graph, you can be passing around, features, projections of features, and so forth, okay? So that's why we're very interested about message passing. So, okay, this is explaining what I told you, just hand waving. So I'll let you go through the slide in case it didn't convince you. Now, as we said, this is the most trivial example. Now let's try to think about that when applied to a tree. So this is our target node that wants to know the size of the tree. So when it reaches the message from the left branch, the node will know that there are 7 nodes on that branch. It will know that there are 3 nodes on this branch. Then it counts itself, and then it passes over the fact that from this point of the tree, there are 11 nodes in total up there, okay? So this can be generalized, and now you can work on more difficult structures. Then it gets also the contribution from the bottom, and now it knows what is the exact size of the tree, which is going to be 14 in total, okay? Okay, so this is the idea of belief propagation, basically. So in this case, the belief word is not appropriate because these are exact values. We're not working with probabilities. But say that instead of this node telling to our target node that I know exactly that there are 3 nodes, this node is performing a sampling in this part of the graph, and it says, I think there are roughly 1 million nodes down here, and I think there are roughly 3 million nodes on the right, okay? So in that case, each node is passing a belief, okay? It's passing what they believe is the size of the graph. And another example you can make now, instead of the size of the graph, you can say, I believe that the right label for you should be 1, and I believe the right label for you should be 0, okay? And in this case, we are doing belief propagation, okay? We're passing around messages, and these messages, instead of telling us what is the size of the graph, will tell us what is the belief that you should be assigned a certain label, okay? So this is the belief propagation 101 explanation that I can give you, okay? First of all. Now, why wouldn't this work correctly with a loopy graph. Can anyone come with an intuition why this is the case? Then I'm going to be showing to you more in detail later. Yeah.
If you go back to the example of the line graph before.
That's a lot of tricks. Yeah, it's gone.
Yeah. But yeah, basically.
There you go.
The reason that it works is because it has to stop at some point. That when you get to one end and say, oh, like there's 5 before me, and then you turn around. But if you kept looping, then one node would basically have 5 before you, and then it would come all the way around.
Exactly.
So like 11 before you, and then 18, and you don't know which one to try.
Perfect. So there are 2 problems you can think of. It's not only that we don't have any halting criterion, because we will just keep on looping in our cycle, but also whatever is the value that we are aggregating is going to be growing or being halved depending on how we decide to aggregate the data. In this case, we're just summing them up. So this number will just grow arbitrarily until we decide to stop the belief propagation, because we allow only, 100 iterations in total, okay? So that's why loops are problematic. We're going to be seeing in a while that in reality, in most of the graphs, these loops happen rarely, or they're big enough that their contribution slowly propagates and leaks, and then it doesn't affect that much the assignment of the labels. But another way in which you can do this, there are a lot of heuristics on how to remove cycles from graphs in a very cheap way. So when in the worst case, you just first remove the cycles, and then you just apply loopy belief propagation. Okay, now let's see how this algorithm works a bit more in detail, okay? So what are the messages that our node I will be sending to J, okay? So this is the scenario that we can think in a generic setting. We have our node I has a set of neighbors, okay? Each one of these neighbors sends messages to I, and now I has to communicate to J and has to tell J, okay, I believe you should be assigned a certain label, okay? So this is the fundamental paradigm of message passing that we were talking about before, okay? So the example of the students that we were just mentioning. Now, let's bring in a bit of notation so that we don't get lost when we take a look at the formula. At the formulas. So the first thing I want you to keep in mind is that we're going to be using this label potential matrix psi or psi, and basically what this value capture is the dependency between a node and its neighbor. So it will tell us what is the probability that a node I being in state yi, given that it has a j neighbor in state yj. So we have been seeing this since the beginning of the lecture, right? We're just calling it now in a different way. It basically captures what is the correlation between node I and node j, okay? We just call it now in a formal way. And now we also bring in a prior, right? So our prior belief is that what is the probability phi of I that our node I is gonna be in state yi, okay? So basically, this is capturing the node features, okay? This tells us what is the prior belief that we have about the node. And our label potential matrix C is just telling us what is the correlation between the labels among the neighbors, okay? So then what we do is we pass messages, so from I to J, and the goal here is to assign a label to J, and what these messages contain are just the estimate that J is being in the state Y of J, okay? So all the neighbors of J are passing a message to it containing what is the estimate that the node should have a specific label, okay? So nothing that is in this slide is a new feature that we haven't talked about. We just label in a different way so that we can come to this, okay? So that we can have a clean formula that explains us what is going on. So let me break it down for you so that hopefully I make your life a bit easier. So as all these other techniques that we've seen today, we start from a uniform assignment, okay? So we initialize all the messages to 1, okay? So no one knows anything about the network. We just know the priors for each node, and we know that all the messages will be to 1. So everyone will have a same probability of being assigned to a certain label. And now for each node, we do the following. We basically send a message, so from I to J, and this message will be the value of this message will be a function of the following. So it will contain, first of all, the label potential. So what is the correlation between the label that currently I holds and the label that he believes that J should be having, okay? So this is basically capturing, is there any homophily between these two nodes, okay? Then, you will also capture what is the prior, so what is the belief that node I should have a certain label. So this is the output of our, let's say, classifier that tells us what is the label that I should be having. And now this last part of the equation is basically all the messages sent by the neighbors from the previous round. So these are all the messages that have been sent to C by all the neighbors of I, so from K to I. So these are all the neighbors except the node itself. And these are all the messages sent to I that contain what is the belief that I should be having a certain label, okay? And this is summed all over the state, so all over the different labels that a certain node can have. Questions? I know this is a bit to digest. Another spoiler, this will be, you will implement this step by step in the homework so that I hope by the end of that you will have a proper understanding of how the message passing works. The good news is it's 4 lines of linear algebra to implement it, so it's not very hard. Question?
L is all the states, right?
L is all the states, exactly.
Can you give an example?
An example of what are the states?
Yes.
Yeah, work with 0, 1. So think of that as a binary label for now. Then the reason why it's presented in this way is because you can generalize it. You can have more labels, okay?
So it's node classification?
Yes, these are the labels basically that you can assign to that specific node.
But in the example before, we have the number of the nodes, right?
Which example before? When I was talking to you about the message passing. Yeah, no, that was just an example to explain what can you do with message passing. And we thought the easiest thing you can think about is count how many nodes are in a graph, right? But now we're not passing anymore how many nodes are in a graph. We're passing what is the belief that my neighbor has that I should be assigned to a certain label. Okay, so they're passing to each other probabilities, basically. Exactly. So you can think of that as a binary label for now, and then you can generalize it. So basically, what you get is a probability mass distribution, and then for each label, you will know what is the probability that it should be assigned to that node. That's how you can generalize it and support multi-class classification in that case. Okay? Okay. Any questions? Yeah.
What is alpha?
What is alpha? What is alpha here, right? Okay, that's a constant. It doesn't play an important role now. Let's not think about it for now. Okay, it basically you can think of this as a learning rate, pretty much. Okay, so depending on what is the value there, you might be converging faster or not, but not to values that you like. So unfortunately, these learning rates appear in a lot of algorithms, so you need to find it yourself. But luckily, most of the implementations of loopy belief propagation come with good values of that already. So you don't have to spend too much time there. Any other questions? Okay, last thing. So now we did our message passing. We reached convergence. Now, after we reach convergence, what is the final assignment of the labels that we make? Okay, so we basically collect all the message that we receive from our neighbors, and then we multiply that by our prior, and then we're gonna be taking what is the class that is most probable. Okay, what is the most probable assignment that should be having based on what my neighbors have been telling me through during the different iterations. Okay, so very similar to what we have seen in all the examples before. The final outcome is a distribution of probabilities, and you pick the highest one and you assign that class. Now, let's go quickly to the example I was making before. We actually already solved it because I wanted you to think about it. But what if our graph has cycles? So the problem there is that messages from different subgraphs are not going to be no longer independent, right? So the example here is, basically we're passing these messages that now they contain some like true or false. Okay, so this is the binary classification. We'll say, okay, there are two neighbors that are telling this node should have a true label, and one node that is telling that this node should have a false label. This message starts to go around, and now when it comes back here, the values are summing up together. Okay, so actually this is a typo here. This should be a 2. Okay, but you can see the problem. Basically, it keeps on going around. It doesn't know where to stop. So the more it goes around, the more these values are increasing. And the problem is that belief propagation is treating this evidence in the wrong way. It's treating it as independent evidence, when in reality it's just the same message that is going around, okay? So it should immediately be able to stop it so that the values are not increasing, okay? So the way in which, clearly this is an extreme example, and as I was mentioning before, likely in practice, these cyclic influences are very weak, because it's very rare that there are so many small cycles. They tend to be larger, so there are some effective techniques on how they can be mitigated. Again, in the homework, you're going to be having an acyclic graph, so no worries about this problem. But I just wanted to mention it to you, in case you try to apply it on a real graph, this is something to keep in mind, okay? So, to recap, advantages. It's easy to program and to parallelize. You would see why you can already think about it, like each node is going to be like an actor, for example, that is sending a separate message. So you can spread an implementation among different cores, or you will find a solution with linear algebra. That's what we will be doing in the homework. It's very generic. It can be applied to a lot of different graphical models. The challenges are similar to what we talked about before. Convergence is not guaranteed, especially if there are a lot of closed loops. So one trick that I can recommend you here is that we have studied it from the first week. Check what is the clustering coefficient of your graph. If it's very high, possibly loopy belief propagation is not the right technique to use there, okay? Now we're going to be seeing that some of these functions that we talked about before, we can either try to learn them. Okay, so like you can imagine that all of this can be learned. Like this can be a classifier, and also this correlation between I and J, this label potential can also be learned. But in reality, in the example we're going to be seeing in the last 2 minutes, you can use prior information that you gather yourself, from domain knowledge or from just observing the data in your graph, and you can have fixed assignments for that. So let me quickly go to the last example. So now we're going to be seeing an application of belief propagation, and this one is in online action fraud, okay? So it's a paper from a bit more than 10 years ago. So why action sites are a very attractive target for fraud? If you go and check the reports from the Federal Internet Crime Complaint Center, apparently 63% of those complaints are related to these auction platforms, okay? So clearly the biggest one is eBay, but there are also a few other that are driving a lot of e-commerce online. So the average loss per incident is roughly $400, so it's a tangible amount of money. And the standard, the most common fraud happening is non-delivery. So someone pays and then the item is not delivered, and they make up excuses and so forth. So this happens more often than you can imagine. So as we said also before, looking just at the individual features is often insufficient, so using just the user attributes or the login times and session history often not enough. What is harder instead to fake is the graph structure, okay? So basically we want to try to see if we can capture relationship between users and if these relationships can help us to identify who are these fraudsters, okay? So our main question is, how do they interact with other users and among each other? We want to try to, do a user behavior analysis of the fraudsters. So how these systems work is that each user has a reputation score, okay? And users are rating each other by feedback, so if I was happy with the transaction that we had, then I'm giving you a positive review, and then my reputation score goes up, or the opposite, if I give a negative one, the reputation score goes down. So how do the fraudsters try to game the feedback system? And you can imagine now they're very much organized because, again, you can earn a lot of money out of these frauds. So they could try just to boost each other's reputation, right? So they will just be doing transactions with each other, but this would be very easy to be caught by the system, right? Because as soon as you start to see that they're heavily connected, they have almost like a click-like connectivity, and few of them are identified by the auction website as fraudsters, then the whole click goes down, right? Because they can quickly find out that they're connected. So what they actually do instead is they form a near bipartite core. So they have they have the actual fraudsters in red, they have accomplices in yellow, okay? And what these accomplices are doing, they try to do most of the trades with the legitimate people on the platform, and then every now and then they also trade with the actual fraudsters to pass basically some of the reputation over to them, okay? So now how do we find the component of this nearby bipartite course, okay? So how do we find the honest, accomplice, and fraudsters? So in this paper they use belief propagation, and now our label potential metrics, as I was mentioning before, rather than needing to learn it, what they've done here, they just set their prior beliefs on the values, okay? And if you go and read in detail, basically this matrix is capturing exactly the kind of interaction I was explaining to you before. So for example, fraudsters interact with each other with very little probability, with an epsilon, but then they have high probability of interacting with accomplices, and then every now and then they interact with an honest user, and that's when they commit the fraud, okay? That's when they don't ship the goods. And the accomplices instead have a similar probability to interact with both honest and fraudsters, and the honest people have similar probability of interacting with accomplices or with the honest people. So what they've done here is in this label potential metrics, they encoded the expectations of how these users are behaving, and then they applied loopy belief propagation, created this toy example, they continue until convergence, and now they're able to find both the fraudsters and the accomplices. And again, I will point you to the paper. It works pretty well. It gives a very good probability distributions. So like in this case, we were talking about how the labels look like. This is not a binary classification problem, for example. So the fact that we can generalize loopy belief propagation means that we can find 3 different labels, okay? So this is a 3-class classification problem. Okay, to conclude very quickly, we're seeing 3 different models today. The relational one, we just average the neighbor properties, but it doesn't use the node attributes while labeling. We're seeing the iterative classification that not only use the node labels, but also the neighbors labels, and it can consider the node attributes while labeling. And last but not the least, we're seeing belief propagation, where by message passing, we update each node's belief of itself based on all the neighbors' beliefs. Okay? So I conclude the lecture here, and I'm happy to take questions even now or offline. Thank you.